reversing and exploiting an Apple firmware update. Okay, so this is the situation that we're in. I'm assuming that you've already compromised a Mac OS X box. This is not like a new method for penetrating a Macintosh. So you've rooted somebody's box. Say you read the book by Miller and Diazovi, which is a great book. You found some 0-day and you exploited somebody, and you want to maintain control of this box. So this guy, Jesse Daguano, he presented a talk on OS X rootkits at Black Hat last year. And so you could use his proof of concept rootkit. There isn't much work on rootkits on Mac OS X. Nemo did some stuff a long time ago on older versions of Mac OS X. Just recently at DEF CON, I guess his name was Bose Erickson. He did runtime kernel patching of the sysint table. But there really isn't a whole lot of publicly available rootkits on Mac OS X. But one thing that all these things share in common is that if the user reinstalls the operating system, those rootkits die. They go away. So the thing is, we want to maintain control permanently. So I suppose whatever vulnerability we use to get access to the box in the first place, Apple releases a patch. And if the person that we exploited, they're very paranoid, and they reinstall the operating system from media, and they safely update the patch level, we want to still, once we've gained access, we want to permanently have access. So how are we going to do that? Well, there are some things that work to our advantage. What Apple does is they like to release products before they've been fully tested. What they do is they use the early adopters basically as beta testers. And then what they do is the products aren't quite ready, but they're shipped. And then they later address bugs and issues with firmware updates. And a few months ago, I went to support.apple.com, and I did a search for firmware update. And at that time, there was almost 1,000 firmware updates available. So that's quite a large number of firmware updates. And one convenient thing about the Mac world is that the Macs, they don't tend to change all that much. Like a lot of machines, they're, hardware-wise, they're quite similar. Whereas in the PC world, things are quite different. Like a Dell and an Acer and HP, these machines underneath are actually quite different. So this is just to kind of show you on support.apple.com. If you do a search for firmware update, there's all kinds of stuff. So what kind of stuff has Apple issued firmware updates for? They've issued firmware updates for graphics cards, keyboards, trackpads, the Bluetooth adapter, all these things. So what we're going to do is we're going to look at the keyboard. So what can an attacker do when they have control of your keyboard? They can pretty much do whatever they want on your machine if they control your keyboard. So this is a picture of a dog just kind of typing at a keyboard. There's an old expression, what is it? Nobody on the internet, nobody knows that you're a dog, whatever. Okay. So if the attacker has control of the keyboard, what can they do? What they can do is they can literally shovel a shell back to themselves. So how do we do this in Mac OS X? We can use Spotlight. Spotlight is by default, installed on Leopard and Snow Leopard. So you type command space, and that activates Spotlight. And the focus is automatically in that box. So you can type terminal, press return, you launch terminal.app, and then you can type that sequence of keys, exec, bind, shell, and so forth, where you replace IP by the attacker's IP and port by the attacker's port number, and then you press return. And what does this do? This literally shovels a shell right back to the attacker. So you can have like a netcat listener, and then you can just literally control that computer. So if somebody has control of your keyboard, that's not a good thing. And some Mac users, they think they're protected because they use some outbound, personal firewall. This Little Snitch, which is a pretty popular product. This doesn't do anything. You can just add, in that keystroke sequence, you can just add a return. And the default option for Little Snitch is just to let the network connection go outbound. So what can we do? If we control the keyboard, what can we do? We can persist the rootkit. So say if our rootkit on this guy's machine is eliminated. The user reinstalls the operating system. What we can do is every time the machine boots, we can actually signal to the keyboard, that we're still running. And then that's say using the control USB endpoint. But at some point, if the rootkit has died and the keyboard no longer receives that signal, then the keyboard knows that it needs to send control back to the attacker. So we can keep a rootkit alive even if the host operating system is reinstalled. And the reason why I have a picture of this guy, Terry O'Quinn, is that he plays, I think his name is John Locke on the TV show Lost. And I don't know if that show is popular around in Europe, but in any case. Okay, so the keyboards that Apple currently sells, there's 3 varieties. There's like, the top keyboard is like a full, like a USB keyboard. It came out in August 2007, and it's about $50. And then they have a Bluetooth keyboard that they came out with at the same time. That's $79. And these are very thin, like aluminum keyboards. And then in March 2009, they came out with a smaller, like a USB keyboard. And just recently, like within the last couple of weeks, they updated the Bluetooth keyboard. Now, the older Bluetooth keyboard took like 3 AA batteries, and now it takes like 2 AA batteries. And I don't know what other changes they've made because I haven't had a chance to really look at it. But as far as I can tell, that top keyboard is the most popular external keyboard because it comes by default with like the Mac Pro, the iMac, and it's the cheapest. I think now the default options have changed, but there's quite a period of years where that was like the default keyboard that came with a Mac, a desktop Mac, that is. So we're going to focus our attention on that keyboard. All right. But in 2007, when Apple issued that keyboard had bugs in it, believe it or not. There were problems with it. And on Apple's support forums, you can still find some posts where people are complaining about various bugs in the keyboard firmware. So like, keys were like, keystrokes would be missing and various, problems that they had. So this one, like, it misses like 1 in every dozen keystrokes. So Apple didn't test this product when they released it. So what did they do? In April of 2008, they issued a keyboard firmware update. This is the first time I've ever heard of a keyboard firmware update. But in any case, so they issued this thing, and this is the URL that you can go to download it. The only thing is recently Apple changed this. Like sometime between my presentation at Black Hat and TourCon, they changed it. But if you want to get a copy of the original, contact me afterwards. So like the original firmware update, it's this .dmg file with that SHA-1 hash. You download it and say copy it to your desktop. That you mount that DMG file, and there's like a .pkg file. And if you double-click that .pkg file, most likely, if you have a keyboard attached, this is the message that will come up if you apply all your patches and so forth. So there's a check in there that whether or not the keyboard has already been updated. But it doesn't matter, we can bypass that. So if you have the Xcode suite of tools installed, you can use this tool, Flat Package Editor, and look inside of .pkg files. You can also use a tool, a shareware tool called Pacifist. So within there, that PKG file, there are 2 other .pkg files. One is for like the aluminum keyboard firmware update, and the other one's for the Bluetooth keyboard. So the first one there, that's for the aluminum the external USB keyboard. So take that payload file and drag it to the desktop. And if we double-click that, then what happens is there's an applications utility, applications directory is created. Within that, there's a utilities directory, and then within that, there's a Cocoa application. And what the installer does is it takes that payload and actually runs it in the root directory. But since we copied it to the desktop, it's created on the desktop. So if you run that Cocoa application, that thing also checks if the keyboard needs to be updated. And if your keyboard has been updated, it refuses to do anything. So the only option there was just to quit. So now what we want to do is, we can look at that Cocoa application. So if we right-click and do Show Package Contents, in Mac OS X, like an application is actually a directory with a whole bunch of stuff in it. And so here, there's a contents directory in Mac OS X. That aluminum keyboard firmware update, that's the actual binary. And then there's like a resource directory, there's a plist file and all this other stuff. So if you want to, learn more about having, if you want to have an introduction to reversing on Mac OS X, I recommend Cameron Hotchkiss' Recon presentation. Okay, so let's look inside that resources directory, and there's a whole bunch of stuff in there. There's a localization languages, and All right, so if we look at the thing that was in the contents Mac OS directory, this aluminum keyboard firmware update, and we look at its magic number, it's Cafe Babe, and in Mac OS X, that's like the magic number for a universal FAT binary. So we're going to look at the x86 binary. So, there's a tool that called LiPo that you can use to like separate the two. That's kind of an aside. So in terms of like when a keyboard is plugged in, there's a tool that in the Xcode suite of tools that's pretty convenient, and that's IO Registry Explorer. So you can look at devices on the USB bus. And I don't know if you can read this back there, but it gives information about like the, the vendor ID, product ID, and all kinds of various things. So kind of like from a high-level view, if we look at these values for like an updated keyboard, there's this BCD device value, ID, product ID, and vendor ID. So Apple's vendor ID is a 05AC, and the US USB keyboard, this thing has a product ID of 0220. And whenever it's been updated, the BCD device value is hex 69, but whenever it hasn't been updated, it's hex 67. So this is the mechanism by which these they can tell that the keyboard has been, whether or not it's been updated or not. That's kind of like a revision number, so to speak. So and if we look at the output of USB view on Windows, this keyboard it has 2 interrupt in endpoints, and the first interrupt in endpoint has a max packet size of 8, and the B interval values for both of them are hex A, so that's like 10 milliseconds. So every 10 milliseconds, these, the host is like querying the keyboard. Okay, so in terms of like tools, in order to disassemble the binary, I just used OTX. I could have used IDA Pro. I don't have a license for IDA Pro. To do binary editing, I use this tool called ED. Okay, and one thing is, I'm not sure if people here are familiar, there's this law in the United States called the DMCA, the Digital Millennium Copyright Act. And this can make like reverse engineering kind of difficult in the US. But one of the things is there's an exception in the law. So if some company has some software product, and then you independently create your own software product, then in order to make your independent software product interoperable with this other company's product, you're allowed to do reverse engineering for the purpose of interoperability. So what I've done is I've created a Trojan for Apple's keyboard. And in order to make sure that this Trojan is interoperable with Apple's keyboard, I need to do reverse engineering. So there's no DMCA violation here. Okay. All right, so now we're going to step into reverse engineering. So that Cocoa application was checking that the keyboard, whether or not it had been updated or not. So there's like this delegate method, application did finish launching, and this thing does like a number of things. It checks the operating system version. It uses the IOKit framework to like find like the attached keyboard. It checks like the validity of this firmware image file that's in the application bundle, and it uses this function that Apple calls CRC32. So just for kicks, why don't we take a quick look at this function CRC32? So here, this is a disassembly of this function CRC32. You see the function prologue, ESI and EBX are saved. 16 bytes are allocated on the stack. So the thing is, the argument to this thing is an NSData object. There's some class method in NSData, and that is the pass, like the actual that firmware image file. And there's message passing in Objective-C. So it's like we get length. Length is called on that thing. And the return value you can see is put into ESI. And then bytes is called on that file, that firmware image file. And that is put into EBX. And then like ECX, EDX, those things are cleared. So there's a very short little loop. So you can see that EDX is kind of used as a counter. And ECX is like kind of accumulating like the values in the file. So then we just keep on checking whether or not that counter finally reaches the length of the file. And when it does, then what ECX has is it has like the sum of all the bytes in the file. So is this CRC32? This is not CRC32, right? This is not even close. So this gives you some idea of like the quality of Apple's code. They just did not understand what CRC32 is, and they didn't implement it correctly. Okay. So in any case, so whenever we were trying to like run the updater, there was a number of places where the version, the firmware version was checked, so we had to patch the binary to disable those checks. So in a number of places, so this is a couple places. So here we make both of those jumps unconditional. Another place, no op that conditional jump. So now those we've disabled the various version checks, and this is what that Cocoa application looks like whenever you plug in a keyboard that hasn't been updated. This is what it looks like. And then what you do is you click that. It has like a couple things, like make sure the power cord is plugged in, all this thing, make sure there's only one keyboard. And when you click that update button, then there's an error message. So there's yet another place where the version is being checked. So we need to look inside the nib file. So if you're familiar with Mac OS X, the nib file encapsulates the user interface of an application. So recently, like within the last year or so, Apple's changed it to like .xib. Now they're .zip files. But in any case, so if we look at that nib file, in the Xcode suite of tools, there's this tool called Interface Builder, and that's used to lay out applications in Mac OS X. So this is a very simple layout. There's just like that one window, and there's that update button. But in any case, we can, looking at the .nib file, we can figure out exactly what code is called when you press that update button. So that little inspector tells you that do update in my main controller. That's what's called. So if we look at that do update routine, like in my main controller, it does like a number of things. It checks that the machine is plugged in. It asks for administrator privileges. Actually, administrator privileges are not, up until the recent security update, administrator privileges was not required to change the firmware update on an Apple keyboard. But I disclosed to Apple at Black Hat that there was a bug in IOKit, so they recently fixed it. So now you do actually need administrative privileges. Before you didn't. So what that Cocoa application is just a wrapper around this tool, HID Firmware Updater tool, like in the application bundle. Like that Cocoa application just asynchronously calls this thing. And it calls it twice, with like the first time with that dash parse argument, and the second time with those arguments. So if we look at this HID Firmware Updater tool, it doesn't have any symbol information. And this is the third place where it checks the keyboard version. It looks at the BCD device, and it won't do anything if it's greater than or equal to hex 68. So, but we can disable that. That's not a problem. So we just no-op that jump of above instruction. And then now we can actually flash the keyboard. We can just re-flash it to like the current version of the firmware. Because I'm going to be pressed for time, I'll do demos. I'll do a demo at the end. Okay. So if we look at that firmware file, it's if we look at say the first 32 bytes, this thing is obfuscated by Apple. You can look at that thing. It's kind of nonsensical. But what Apple did was they basically just screwed up. So what happens is that firmware image file, it's de-obfuscated on the machine, and then whenever you're doing the firmware update, the unobfuscated firmware image is sent over the USB bus to the keyboard. So what we can do is, the HID firmware updater tool does this de-obfuscation for us. So that's very convenient. So what we can do is, we've taken over a Mac. We take this obfuscated firmware image from file from Apple. Then we can, because that thing, the HID firmware updater tool unobfuscates it for us. What we can do is we can set a breakpoint at an appropriate place. Like we attach a debugger to that HID firmware updater tool. Set a breakpoint at the appropriate place, and then modify that firmware image file in memory, and then send the basically add our Trojan there, and then send the Trojan firmware image file to the keyboard. And when we do that, then we also own the keyboard too. Okay, so let's take a quick look at how Apple did the obfuscation. It's just terribly done. It's just hilarious. So let A be this 83-byte sequence, and let B be this 53-byte sequence. Then this is what the de-obfuscation algorithm starts off with. It reads like the firmware image file, like an 83-byte blocks, and then it does this thing. And then it does further stuff. This is not cryptographic, obviously. It's It's just some crappy obfuscation algorithm that they came up with. And okay, so I won't discuss that thing further. It's just they just did a crappy job. So, and it's a truism in computer security. Don't do security through obscurity, but that's exactly what Apple did. So this is a screen grab from the movie Office Space. Hopefully everybody has seen this movie. So, okay. So, so we can take that unobfuscated firmware out of memory very easily when we're running this tool. So we attach GDB to that tool, set a breakpoint at that address, and then whenever we run it with those arguments, then we can just dump the unobfuscated firmware out of memory very easily. So this is what it looks like. This looks a little bit more regular if you see this red. So I'll explain exactly how this thing is like formatted. What it does is there's like 3 bytes followed by 32 bytes, 3 bytes followed by 32 bytes, and so forth. So, okay, so now we need to figure out how does this firmware update get sent to the keyboard in the first place. So the keyboard, it doesn't have an interrupt out endpoint. It only has like a control endpoint, endpoint 0, and then it has like these 2 interrupting endpoints. There's no out endpoint, so there's no way that the host can, it doesn't use the interrupt endpoints to send the firmware image. What it does is it has to use the control endpoint. And that function in HID firmware update, hex 20C3 does it. And what it does is it calls this, in IO USB device class, it calls that routine. So luckily, what we can do is we can just set a breakpoint there and then just look at the arguments and then figure out what's going on. Because what I don't have is I don't have like a USB analyzer, So okay, so we attach GDB, set a breakpoint there, run, and then we can look at the arguments, and we can go to opensource.apple.com, look at this USB, the source, their USB stack. And so we look at this struct for the IO USB dev request. We can like pick this thing apart. So this BM request is hex 21. Then there's a B request. This is like if you look at the USB standard, this is like a set _ report request. Then the next thing is this W value and has these values. This index value is 0. The length is just 1, and then the actual data that's just sent is just hex A. And so in order to put the keyboard into like a bootloader mode, what you do is you just send like a set report to the keyboard, to the control endpoint with these values. And then what happens is that the keyboard, it was originally a keyboard, and then it drops off the USB bus, and then it re-enumerates as this keyboard bootloader. Okay, and this is a little bit hard to see. This is the output of a USB prober, I think is the name of the application. So it has like, it has an interrupt in and out endpoint. And so now the keyboard has actually, it's now like this, it's no longer a keyboard, it's this KBD space bootloader, and then we send the firmware update to this thing. So we can look at the stuff that's being sent to this keyboard. We set the breakpoint in the appropriate place and see what's being sent. So we can completely reverse engineer this thing. It's actually very simple. So the commands to the bootloader, this bootloader password, like how the data is formatted, how the checksum is calculated, and the return values. All of this can be determined. So why don't we quickly look at like an example of I call them packets, but I don't remember what the exact USB terminology, but it's kind of like I'm just using packet as kind of it's not like an official USB term or anything. So if you look at this, the data that's sent to that keyboard bootloader, the first 2 bytes, that is the bootloader command. And there's 4 possible commands. FF38, like to enter the bootloader mode, write to flash memory, verify flash memory, and exit bootloader. Those are the 4 possible commands that I was able to determine. And then the next 8 bytes is like a bootloader password of sorts. So, and that's what the password is. It's just 0, 1, 2, 3, 4, 5, 6, 7. If you change any of those values, then it assumes that something is wrong, and then it'll quit. So that's the bootloader password. And then the next 2 bytes is a block number. It's like we're writing to flash memory, and you can't just write like a single byte of flash memory. You have to write like a block. And the block size is 64 bytes, and you're sending it over a half block at a time. So there's a block number. And then the next byte is either 0 or 1, depending upon whether or not you sent the top half or lower half. And then the next 32 bytes, that's like the half block. And then the next byte, all that is just a sum of all the previous bytes mod hex 100. So you send this thing across, and then there's a value that's sent back. And all you have to do is just look at the first byte. And we can completely determine all the possible return codes. These are the return codes that I could determine. So hex 20, that means there's no error. These are other possible things. Say, for example, like if you make a mistake in the checksum calculation, then you get like a communication checksum error. Okay, and the thing is, so each one of these packets has a checksum, and then there's yet another checksum at the very end. And so what that checksum is, it doesn't checksum over like the metadata, so to speak. It's just over the various half blocks. So all we do is we just keep adding up all these possible half blocks. And you see, like that first 32 bytes, that sum is B89, and then the first 64 bytes is 166E. And then we add up the whole, like the whole firmware image. Then that sum is 4E41B. Then what we do is in the very last write packet, right before the checksum for the packet, we put that application checksum where we mod it by hex 10000. And we store that in a big Endian format. So that's all there is. Each individual packet has a checksum, and then the whole thing has a checksum. And one thing is there's no cryptographic checksum here. And this is literally everything. So they didn't do any code signing. And this is what makes the whole hack possible, and Apple's failure to do any kind of remotely decent code signing. So now we understand how the firmware update process works. In order to be able to tamper with it and install malware, we have to kind of look at the underlying hardware. So if we open up the keyboard, this is what it looks like inside. This thing is not really designed to be taken apart. There's like glue and all this stuff there. Yeah, there's no screws. Some people think that you can remove these things and there's screws underneath. There are actually no screws. It's glued tightly together. So let's take a little closer image. So there's a USB hub there. On each side of the keyboard, there's actually like USB ports. So there's a hub, there's a ribbon cable, there's a serial EEPROM, and then there's a microcontroller. So let's look at the microcontroller. So it's from Cypress Semiconductor. It's an 8-bit microcontroller. It has a Harvard architecture. And there's not a lot of space in this microcontroller. There's 256 bytes of RAM and 8K of flash. So I think what Apple did was they must have like the exclusive rights to this chip now, because if you go to Cypress and you want to buy this chip, or you want to request a sample, they won't send you one. And the data sheet is no longer on Cypress's website. But I was able to find it online. Okay, so just quickly look at the architecture of this thing. The program counter is 16 bits. In order to be able to address 8K of memory, it can't be 8 bits. It's got to be more. Then there's an accumulator, which is like just a general purpose register. There's an 8-bit stack pointer, and on this architecture, the stack grows upwards. There's like this index register that's used to like hold offset values, and there's this flags register. And there's not a whole lot of flags in this thing. It's not like E flags or anything. So the flags register is just 8 bits. There's like there's a bit for whether or not global interrupts are enabled. Like depending upon the result of the last arithmetic calculation, you have like a 0 or carry flag. And this thing actually has a special state, the supervisory state. And this is kind of like this is a special state where, that's whenever you're actually writing to flash on the microcontroller. That's what that supervisory state bit is. And in order to mess with the flags register, there's actually special instructions for that. Okay. All right, so, and then for the interrupts for this thing, these are the interrupts. And I don't know if people can read that. It's not real important. So they have the special supervisory system call. And this is what is kind of unusual about this chip, that it can just change its own flash. And so it has a number of like functions. And what's most interesting to us is that write block function. So if we set these various registers to various values, we can actually, the chip can change its own flash. It's really quite cool. So whenever you're dealing with like a USB product, there has to be, whenever you're like developing a USB application, there's like some separation of like what the firmware does and what the serial interface engine of the microcontroller does. So this Cypress chip, it takes care of like putting data, translating, formatting data, like computing the CRC stuff, the device address checking, that 7-bit value that each USB device gets, handshakes and all this stuff, the annoying like bit stuffing and unstuffing. That's what the serial interface engine takes care of for us. What the firmware has to do is has to take care of enumeration, filling and emptying like the FIFOs and these kind of things. Another chip on that little board is there's a serial EEPROM. It's an SPI serial EEPROM. This is very much just a commodity part. Oh, okay. And then there's this USB hub controller. So this thing could support up to 4 ports, but Apple just uses 3. So what happens is one of them is wasted, one of them the keyboard is plugged in, and then the other 2 are on the sides. And that EEPROM is used to configure this thing. The vendor ID, product ID, and various stuff is put in there. So this keyboard is actually a compound device. We have like the upstream USB connector. We have the hub, the EEPROM, which configures the hub, the 2 USB ports on either side. 1 USB port is wasted, and then the keyboard itself is plugged into one of the ports. So I need to skip some slides. These are not real. Okay. So when we look through the unobfuscated firmware image and we like disassemble it, this is what we get. And in the very beginning, what we have is a relocated interrupt vector table. So we just look at the first couple of values. There is I want to skip various things. Let me skip that. Okay. Actually, you know what? Maybe let me skip these things. What I've done is I have like a number of exploits that I've released. One is just changing the LED on the keyboard. It's not a big deal. Another one is changing like enumeration, changing like a vendor string in enumeration. These are kind of really just kind of lame, actually. So okay, so now the thing is, if you look at that firmware image, if we look at this instruction set, hex 30 is the halt instruction for this microcontroller. And so here I have this image. Wherever it's red, that's hex 30, and wherever it's blue, that's anything but hex 30. So you can see that right in the very middle, there's all these halt instructions. And what that is, that's free space. So we can use that free space for whatever we want. So let me quickly remind you how interrupt transfers work on USB. So here, what's shaded, that's what the host does, and what's white, that's what the USB device does. And so here, for this keyboard, we don't have any interrupt out endpoints. So only the left-hand side of this figure is what's important. So we have and remember, USB, it's completely like host-centric. The host does everything. So like the host sends an interrupt, it sends an in token to the keyboard, and what the keyboard does is it does one of these 3 things. Either sends data back or sends a NAC or a stall, and it shouldn't send a stall unless there's some problem. So like what the keyboard is doing is the host is constantly querying the keyboard at least once every 10 milliseconds, and if the user hasn't done anything, then a NAC is sent back by the keyboard. But if like the user has pressed the key, or lifted up the key or whatever, then the data is sent back to the host, and then the host acknowledges this thing. And this is kind of like a simplistic view, actually, because the keyboard is plugged into a hub, and then the hub is actually high speed. It's actually a high-speed bus. So there's like C splits and S splits and all this like translation and stuff. But this is for our purpose, from the point of view of the keyboard firmware. This is good enough. So, an in token comes in, we either NAC it or send data back, and then the host acknowledges it. So what we can do is, what's of interest is like intercepting keystrokes that the user types and sending our own keystrokes back to the host. How do we do this? It's actually very easy. All we do is the endpoint buffers. All we do is we just, there's a routine that fills that buffer. We can just modify that routine and do whatever we want. So, this range of register values, memory values like hex 58 to hex 5F. This is the FIFO for interrupt for the interrupt in endpoint 1. I have 81 written there because it's a standard that when you have when you have in, then the high order bit is set. It's the first interrupt in endpoint. So these memory these memory locations in the microcontroller, they see all the keystrokes that are being typed and stuff. So just so it's clear what I'm talking about, I took a Windows Vista box, and I've got USB Lizer running on it, and I plugged in the keyboard, and I pressed the return key, and I lifted it up. So that first sequence of 8 bytes, the 0, 0, I think that's 28, I think it is, yeah. 0, 0, 28, 0, 0, 0, 0, 0. That's when I pressed the enter key down. And then when I lifted that, my finger off of it, then the 0, 0, all zeros goes across. So that's exactly the FIFO for that interrupt in endpoint. Okay. So in the very beginning, I was talking about shoveling a shell back to ourselves, using command space to launch Spotlight and so forth. So this is what we would actually see. We'd have the command press down, space press down, command lifted up, and then space lifted up. This is what the buffer looks like. Then when we type, we type T, press T down, lift it up. We have those 2 lines. Press E, lift it up. Press R, lift it up, and so forth. This is what's actually happening. So okay. And so there's a routine that's in the firmware that actually copies stuff into the endpoint buffer, and this is the routine. So in the firmware, it's calling this routine whenever it has there's some memory, the keyboard firmware has to decode this matrix and then figure out what key was pressed and so forth, and there's a memory location where that stuff is stored. So that address, that address is put into memory location, which one is it? I guess that's X. And then 32, we copy, this routine is used for more than just the keystrokes. It's also used for enumeration and various things. So 32, we put in the endpoint number. So when we're actually dealing with the keyboard function, we put a 1 there. 33, we'll have 8. And I meant to have a comment for 22, but it doesn't really matter. So this is from Apple's firmware. This is the routine that does the heavy lifting, so to speak. Okay, so this is all done. So actually, let me forget this. Okay, so this routine 0D51. Whenever the user presses a key or lifts a key on the keyboard, this thing gets called every single time. So this is what we're gonna want to do is we're gonna want to patch this thing. This is kind of like hooking, in rootkits and stuff. So this is what the left-hand side, this is what the original firmware looks like, that routine 0D51. And remember, at hex 1000, we have all this free space. So what we'll do is, that instruction as 0D51, what we'll do is we're gonna just jump to the free space. And then in the free space, we put this code here. One more thing I wanted to say is, what I'm doing here is I'm actually explaining this. This is actually a really lame exploit. I'm just trying to explain this. What it is I'm just disabling the W key on the keyboard. I'm showing how to do this. This is just as an illustration. Okay, so we jump to the free space, and in the free space, what we're doing is we're looking at location 67, and we're comparing it to 1A. So if, 1A, that corresponds to the W key. So if it's not if it's not the W key, then we go to 1008. So that's like what was originally there. If it's not the W key is not pressed, we just do what we were originally supposed to do, and then we jump back up to that 0D57. But if it was the W key, then that instruction at 1005 is executed, and we just overwrite it with 0. So what this does is this effectively disables the W key. So this is just for this is not there's nothing really important. All right, so what we can also do is we can also intercept the keystrokes and store them. So we can this is like the main payload. It's a firmware keystroke logger. So here, the way that this keystroke logger works is that I didn't want to make a tool that could be immediately used for attacks. What I do is the keystrokes are coming in, and I look at what I do is I'm storing like the keystrokes that the user types in the FIFO that the endpoint buffer that backs the second interrupt in endpoint. So there's a very small amount of space there, and but the only thing is in order to retrieve that stuff, I use the return key. So I store stuff there, and then I use the return key to retrieve that stuff. So what I have to do is like hex 28, see in 1006, I have to check whether or not the return key was pressed. And depending upon whether or not it was pressed, there's one of two sets of code that's executed. I really want to do this demo. So this is this is like a firmware keystroke logger. So let me demonstrate this. Okay, let's see. Whoops. Okay. All right. So just so you can see that this this keyboard is working okay. Oh, sorry, it's not plugged in yet. Okay. So it's everything's working okay. So now what we'll do is I'll attach GDB to it. Let me see. I need to. Whoops. Where did it? Oh, it's over here. Sorry. One thing is I had like a 75-minute slot at Black Hat, so that's why, and I only have a 50-minute slot here. So these other demos I can't do.
You have the last session, so if everyone agrees, you can continue.
Oh, okay. So let me.
If you want to stay.
Okay. Let me, so this is the firmware keystroke logger. So I've attached GDB, and then, so now I just, what I do is I set a breakpoint at the appropriate place, run it, it hits the breakpoint. The firmware image has been unobfuscated in memory, and then I change the firmware in memory. And then now the new firmware image is going across the USB bus. And, okay, so now I have installed a firmware keystroke logger in this thing. So let me demonstrate this. What do people want me to type? I can type anything. DeepSec, so let me say, okay, so DEEPSEC. So remember, I use the return key to retrieve things. So everybody sees that? I'm doing it in reverse chronological order. Does everybody see this? What I've done is I took I take the keystrokes and I store them in this the FIFO that backs the interrupt in endpoint 2, and then I use the reason why I use the return key to retrieve the keystrokes is because if somebody takes this and then tries to use it right away, somebody will realize there's a problem when the return key doesn't work correctly. There's a reason why I do that, just so I don't get myself into any kind of trouble. Okay, so let me. Okay. All right. So so this is like this was a proof of concept keystroke logger. Like it's deliberately neutered. I use that FIFO buffer. It really wouldn't make sense to do that. What you would really want to do is you really want to store it in RAM. That's where if you want to make a weaponized keystroke logger, that's what you would do. So I've neutered it because you have to use the return key to retrieve the keystrokes. It only stores a small number of keystrokes because it uses that 8-byte buffer. But if you wanted to, what you could do is that free space, and using that supervisory system call, you can actually write keystrokes to that flash. You just have to make sure like that the checksums will, that the whole application checksum still works. And you can write a keystroke logger, a firmware keystroke logger that stores like 1,000 or so keystrokes. So this could be useful, like say, if you wanted to steal somebody's whole disk encryption key. Because if you've owned their box, then you may not want to like, I guess in memory, like the key schedule might be there, but it might be painful to recover the actual whole disk encryption key. So you can, this would be one way to do it. So other stuff, do we need physical access to get the keystrokes out of the keyboard? Actually not. Like there was, like the academics like thought about this a while back. And so Matt Blaze at the University of Pennsylvania, he had a paper where if you had like a keystroke logger, like a hardware keystroke logger on somebody's computer, and you weren't able to get physical access to that computer again, how would you retrieve the data? What they did was they introduced timing delays, and then they exfiltrated bits of data over interactive protocols like SSH, VNC, and so forth. And yeah, don't use Apple keyboards. I don't use Apple keyboards, period, actually. So like the thing is, like one of the things is, suppose like, even though these are nice little thin keyboards and stuff, if you use it in your data center, there could be very unusual attacks would become possible. So, okay. And the natural question is, what about the keyboards in MacBooks and MacBook Pros and so forth? They also have the same problem. The exact range of vulnerability, that I don't know. I don't know exactly when Apple introduced this problem, but it's like this is like a pre-aluminum unibody MacBook, a pre-aluminum unibody MacBook Pro. This thing, the keyboard, the firmware here is vulnerable. So probably within if I had to make a guess, I would say probably when they switched to the Intel platform, that's when Apple really screwed up. So we have this situation. A remote attacker can install a keystroke logger right into the firmware of your keyboard, your laptop keyboard. Because like the keyboard in the MacBook Pro, it is a USB keyboard. If you use IO Registry Explorer, you see that there are actually a number of devices on the USB bus. The iSight camera, the infrared device, the Bluetooth adapter, those are all USB devices. The keyboard, a USB device. So like, okay. And one thing is, whenever you're writing your own firmware, you can kind of mess up kind of easily. What happens, the most common mistake that I would make is I would make a mistake in the application checksum. So then what happens is then the thing is the keyboard is in a bootloader mode. So all you have to do is, in order to get around this issue, you just have to change the hex 220 to hex 228. And by the way, the hex 220 for the keyboard, the external USB keyboards that Apple sells in the United States, that's what the product ID is. And I have received email from people that it's different in like some countries in Europe. It's like 221 or something. Everything holds is the same. You just have to change these various values. But if we wanted to be malicious, we can also intentionally brick a keyboard. And it can be done in such a way that the keyboard is completely hosed and the bootloader cannot run. Like it can't even enumerate. And the way to do this is we can do this with just one appropriately placed jump. It's just hilarious. If anybody wants a demo of this, I'm happy to give the demo. And just it'll cost you like $50. You have to bring your own keyboard. I don't want to mess up my own keyboards. So I say that Apple needs to fix this. And the reason why is that because suppose somebody has like a Safari O-Day, what you can do is you can craft like a web page, and whenever a Mac user visits that web page, boom, you can just brick their keyboard. If for the desktops, it's not so bad because you can plug another keyboard in, but for the laptops, it really sucks because it doesn't suffice just to replace the keyboard. That Cypress chip for the laptops is actually on the logic board. So then the so-called geniuses in the Apple Store, they're not going to be able to fix that. They're just going to put a new logic board in there. So the only thing is now, because of disclosures I've made to Apple, it's a little bit harder to do this because you have to be root now. Believe it or not, up until like up until just a couple weeks ago, you only needed to be an unprivileged user can change the keyboard firmware on a Mac. It was just like literally, if you had like a Mac OS X server, and then like you could have like just a regular user can just boom change the keyboard firmware. It was just a terrible bug in IOKit. It's just hilarious. In any case, so you could also, as I was saying before, you install your malware into the keyboard. You can mess with the firmware update, and you can pretty much own that computer like forever. So a couple of people I want to thank: Ben Fransdale, Script Blue, King Lee, Scott Moulton, Nathan Rittenhouse. Okay, so are there any questions? Do people want to go back over the slides that I skipped over? I'm happy to talk about it afterwards with anybody. With all those slides that I skipped over, all it is just just playing with the LED light emitting diode here, and messing with enumeration, and then just disabling keys on the keyboard just for kicks. It's nothing really fancy. Yes, a question.
Two questions. One, what was Apple's response besides issuing the IOKit update? And second question, a few years ago, there was a Windows-based rootkit who installed itself into the PCI bus firmware. And do you have any further ideas where to hide Mac-based rootkits besides the keyboard?
Okay, so the first question about what was Apple's response is, I'm not really sure that they can fix this. One of the things is because of the way the lock bits are set on these certain blocks. So what they could do is, for the laptops at least, what they could do is they could just do a recall of all the laptops. And then I believe there are probably test points on the logic board where they can reprogram the keyboard firmware. That's one thing that they could do. Or they could have these little devices that are used in prototyping to connect to the pins of that chip and then reprogram it. If it was like a BGA packaging, then Apple would be in trouble. But it is possible for Apple to fix it, just that it would cost a lot of money, and I don't think they're going to do it. And your second question was about what other places for rootkits. Yeah, I've been looking into that. You were saying something about, what was it, a PCI or something?
Yeah, as far as I remember, it was like 4 years ago, a PCI-based rootkit who installed itself into the PCI bus. I don't remember.
Oh, are you talking? I think you're talking about like John Heisman's stuff. Yeah, what did he? I think his stuff was like using like ACP and these kind of things. One of the things is like Macs, like the boot up process is different from PCs. Apple, for whatever reason, they must have gotten bamboozled by Intel, and they use EFI and stuff. I'm not sure about those kinds of. To tell you the truth, I'm not really very familiar with EFI. So like, yeah, I would just ask John Heisman. Are there other questions? Yes.
Is this upgrade process also controlled by this application on the chip in the keyboard? Because if you can disable as an attacker, if you can disable the update, then my question is whether Apple could improve this process by implementing some kind of signature, if possible, like signing the code of the update.
For like the keyboards that are already out there, I suppose they could push out an update, and they could disable further updates. That is one thing. But if like the attacker has already put their own code in there, if I were gonna like do this to somebody's keyboard, I would change like the vendor ID and product ID and make it look like there's some other keyboard attached, and then there's nothing that can be done for that person. They're screwed. And I think they probably. One of the things with these external keyboards is that you can't take them apart easily. If you're going to take it apart, it's going to be damaged. So you can't just attach things to test points or attach things to the microcontroller. You have to do it through this bootloader. And I haven't like really tried to do it myself. It's there's they may or may not be able to do something about it. I'm not sure. I don't know if I answered your question. Okay. Are there other questions? Okay, so if anybody, if you have your laptop and you want to play around with this thing, feel free. I'm very happy to demo this thing. Okay. Okay, thank you.